You know, everything in our modern world, from the phone in your hand to the engine in your car, it's all built on a really simple but incredibly difficult idea, making things the right size. It sounds so obvious, right? But behind that simple concept is this hidden science of just, well, staggering precision. Okay, let's get into it.
So take a look at this shaft right here. This is a perfect example. Every single gear, every groove, every smooth surface, it all has to be made to an exact dimension so it can fit and work with all the other parts. If it's off by even a tiny fraction of a millimeter, the whole machine could just stop working.
And that really leads us to the most important question of all. How do we actually measure something with enough certainty to build our entire world on it? I mean, how do we even know what the right size is in the first place? Well, the answer comes from a field of science you've probably never even heard of.
And that field is called metrology. It's quite simply the science of measurement. You can think of it as the official rulebook that underpins all of engineering, all of manufacturing, and really science itself.
So what does that really mean? Well, at its heart, metrology is all about taking a physical property, like length or weight or time, and assigning it a specific number. It's the process of turning the physical world into data that we can actually trust and work with. Now, to really speak the language of metrology, we've got to get two key terms straight, because they get confused all the time, but they mean totally different things. And those are accuracy and precision.
Think of it like this. Accuracy is all about hitting the bullseye. It's how close your measurement is to the actual true value. Precision, on the other hand, that's about repeatability. It's hitting the exact same spot over and over and over again, even if that spot isn't the bullseye. And in manufacturing, you absolutely need both. No question.
Okay, let's go back to our shaft. In a perfect world, on the blueprints, this part would have what's called a nominal size. Let's say it's 63.5 millimeters. That's the true value we're aiming for. It's the absolute perfect dimension.
But here's the thing. Manufacturing is never perfect. So what engineers do is they define a tolerance, basically an acceptable amount of wiggle room. In this case, the part is considered good if it's within plus or minus 0.08 of a millimeter. That is an incredibly tiny margin for error. It's the kind of thing that separates a working jet engine from a total disaster. So how on earth do we measure that?
Well, let's climb what I like to call the ladder of precision. We're going to start with the most basic tools and work our way up. And the first rungs are the good old ruler and its more sophisticated cousin, the caliper.
We've all used a steel rule. It's simple, it's effective, but its accuracy has some serious limits. Get this, on a good ruler, the little black marks themselves are somewhere between 0.12 and 0.18 millimeters wide, so you're already limited by the thickness of the very line you're trying to read.
And then, of course, there's human error. The biggest culprit is something called parallax error. It's basically the way things seem to shift depending on your line of sight. To get a decent reading with a ruler, you have to hold it flat against the part and look at it from directly overhead, straight on.
The source material gives a fantastic way to think about this. Try reading a clock with a second hand from way off to the side. The hand will look like it's pointing to a totally different second than it actually is. That's parallax in action, and it can easily wreck your measurement.
So, to get around some of those problems, engineers use calipers. Now, these aren't for reading a measurement directly. No, they're what you call transfer devices. You carefully adjust them to the size of the part, lock them, and then you hold the caliper up to a ruler to get the number. This is a clever way to help cut down on those tricky sighting errors.
And here's the crazy part. Using simple calipers isn't just about what you see, it's about what you feel. Getting the pressure just right, not too loose, not too tight, is a skill. It's a highly developed sense of touch that can only be learned through years and years of practice. It's a really surprising human element in this world of pure precision.
But what if we could take some of that human guesswork out of the equation? Well, that brings us to the next rung on the ladder, a really brilliant invention called the vernier scale.
This right here is a vernier caliper. It basically combines the jaws of a standard caliper with a much smarter way of reading the measurement directly on the tool. And not only can it measure outside dimensions, like the old ones, but it can also handle inside dimensions, which makes it way more versatile.
The fundamental problem that the vernier scale was designed to solve is this. With a normal ruler, when your measurement falls somewhere between two lines, you're just guessing, right? Is that 0.4 of a millimeter, 0.5, 0.6? How can you possibly know for sure?
Well, the absolute genius of the vernier is this little sliding scale. See, its markings are spaced just a tiny bit differently than the markings on the main scale. And because of that tiny difference, as you slide it along, Only one line from the sliding scale will ever line up perfectly with a line on the main scale. That one single point of alignment, that's what gives you your precise decimal reading. And taking a reading is actually a pretty simple three-step process. First, you read the whole number of millimeters on the main scale. Then, you just scan your eye across that sliding vernier scale to find that one line that lines up perfectly. You read the number on that line, and that's your decimal. Add them together, and boom, you've got your measurement.
So when you boil it all down, the vernier scale is designed to do one thing and one thing only, to turn an estimate into a confident reading. It changes a subjective guess into an objective fact, which, let's be honest, is the entire goal of metrology.
But we can go even further. For the absolute highest levels of everyday precision you'd find in a workshop, we have to actually magnify the measurement itself. And for that, we need the micrometer.
This is an external micrometer. You place an object between the fixed part, that's the anvil, and the part that moves, which is called the spindle. Then you turn the thimble at the end, and as you do, the spindle slowly closes in on the object, which lets you make incredibly fine adjustments.
The micrometer works on a brilliantly simple principle. There's an incredibly accurate screw thread inside. That means that one full turn of the large, easy-to-read thimble moves the spindle forward a tiny, very precise distance, usually just half a millimeter. You are mechanically amplifying your own movement, which makes reading those tiny, tiny fractions of a millimeter incredibly easy.
So we've gone from the simple thickness of a line on a ruler to the practiced, subtle feel of a craftsman, all the way to the pure mechanical genius of a screw thread. Each step up that ladder is a quest to get rid of uncertainty and get closer to the absolute truth. It really makes you wonder, doesn't it? Where else are these hidden principles of precision secretly shaping the world all around us?